Okay, so last time we learned about what adjoint of a map is. So we defined something like if you have T, U, and V, there's this adjoint of T that allows you to move this T to the other side. So, so for any T, a linear map from U to V, there exists a unique adjoint from V to U such that this above is true. Okay, and that was defined for general maps, but today we're going to only focus on operators. Operators is a special kind of map where domain and target is the same. So we'll begin with a special kind of operator. So 7.11 definition, and the definition is for T, an operator on V, okay, if T star is same as T, then we say T is self-adjoint. Okay. I mean, the choice of the self-adjoint makes sense because it's T star being equal to T means that the adjoint of itself is just itself, right? So it's an obvious definition. And another thing that you have to look for is that since if U and V are different, then the T star will be from V to U, not from U to V. There's no way for these two to be equal. So this self-adjoint definition only makes sense if domain and target are equal, which means T has to be an operator for this to be to make sense. Okay. All right. Now, in mathematical physics or in some other like function analysis and stuff like that, this self-adjoint has another very widely used name. It's also known as Hermitian. The Hermitian matrices are very important in quantum mechanics because in quantum mechanics, observables are operators and vectors are the states. And when you operate an operator on a vector, and then you represent the output as linear combinations of the eigenstates, eigenvectors. And another thing that we will eventually prove is that Hermitian matrices have orthonormal basis of eigenvectors. Okay, so you have these normalized eigenvectors, which are the states of the system, and then anytime you want to observe something, you operate this. So let's say you have a Hermitian operator for momentum of a state. Then what you do is you operate the momentum operator to the state, you get a vector, and you represent them as linear combinations of these orthonormal states, and then you get different values, different eigenvalues, right? Yeah. So these different eigenvalues are the different possible values of the momentum for that state, okay, with certain probability, and that has to be figured out separately. That's what it means. Okay. So Hermitian operators are very important. Now, often, whether it's self-adjoint and Hermitian, people just say these are matrices which is equal to its conjugate transpose. Okay, So that's another definition you would see rather than this cryptic definition of the adjoint is itself. And the reason for that definition is because of something that we learned last time, which is that we learned that there's a relationship between the matrix of the transpose and matrix of itself, and it's that they have this relationship. The original matrix and the matrix of the adjoint operator has the property that it's conjugate transpose of itself. Now, underlying this, what I'm not really saying is that, you know, every matrix, to write a matrix, you need to choose a basis, right? So in the case of basis for U and V, let's say B1 and B2, basis for each one of those, you really need to write down T of B1 and B2, and if only when those two bases are orthonormal bases, then this relationship happens, okay? Now we're working with an operator, so you don't need to have two different bases, you just have a single basis, okay? So if I write the basis explicitly, we're really saying the following. You have a basis which is some basis, and this is orthonormal. And under that basis, these two matrices, the matrix of the original matrix and the adjoint, as a relationship that one is the conjugate transpose of the other, okay? Therefore, under this theorem, you can see that another way to say that a given operator is self-adjoint or it's Hermitian is it means that you have conjugate transpose of the matrix. If you write down the matrix for that operator under some orthonormal basis, then its conjugate transpose is equal to itself. The first very important theorem, and this is basically a reason why in quantum mechanics they require that all the operators are Hermitian, is because the eigenvalues of a Hermitian operator is real, and you really want to extract real numbers from quantum mechanical calculations, and being Hermitian basically guarantees it. So this next theorem is probably the most important theorem that you should know for any self-adjoint or Hermitian operators. And by the way, I'm really going to expect everyone to memorize this proof because it's so easy, okay? So let me first write down the statement. The statement is 7.13. All eigenvalues of a self-adjoint operator are real. Okay? So let's see why that is. So proof, let lambda be an eigenvalue of t with t equals to t star. Okay? So you have a t is self-adjoint, this is what it means, and lambda be an eigenvalue of t. Now, what does it mean to be an eigenvalue? Eigenvalue, by definition, it means that you have a non-zero vector v where tv is equal to v for some v in v, and v is non-zero. That's what it means. Okay? So let's try to figure this one out. So lambda times norm of v squared is lambda times vv. So this was one of the properties of the inner product. Once you have an inner product, because it's positive definite, you can use it for the size of a vector. And in fact, when this is the usual dot product that you learned in multivariable calculus, it does give you the norm squared, right? So suppose you have this, then you can move this lambda inside, where because lambda v is tv, you can rewrite this as tv v. And the whole purpose of adjoint is to move the operator to the other side, right? So other argument of the inner product. So we're going to move this t to the other side. Other argument with the star. But t star is t, so I can rewrite this as tv, which now becomes v lambda v, right? But what did we learn about the second argument of an inner product? The numbers come out as conjugate. Yeah, complex conjugate. So you get lambda bar vv, so you get lambda bar v. Now since norm of v is non-zero, since v is non-zero, norm of v is non-zero, therefore you end up saying lambda is equal to lambda bar. Okay. I wrote rather a detailed proof. You know, you really don't need to write this. You can say let lambda be an eigenvalue of t. Then you can even delete this and just start from here. Start from here, and this equal to this equal to this, and then you can just skip over this and write this, because self-adjoint means that you can go to the other side without having a star. And then, yeah. So how many equations is that? It's like 1, 2, 3, 4, 5, 6, and then done. Okay? There's a very simple proof. You should memorize this by heart, because I'm going to put on the exam. E is self-adjoint if and only if TVV is a real number for all V in V. Now to prove this, you have to start by 7.15. It will be a lemma for this, 7.16, which says that TV V equal to 0 for all V and V is same thing as saying that T is 0. Now, hidden in this proof, there's an additional comment that it's going to refer that we probably proved some time ago. I can't remember when, but this is something that we use a lot, that if uv equals to 0 for all v, then u is 0. Okay. Now this, maybe we didn't even prove this. This is kind of like straightforward, because if this is true for all v, then you can specifically choose v as u itself, right? Then this implies that u is also 0, but then by the definiteness of the inner product, that forces u to be 0. Okay, so that's what we're going to do. And what we are going to do as a proof, we're going to say that if I have tu and v, w, sorry, tu and w, I want to rewrite this into something really complicated, but in a way that it looks like this. Okay, so these two vectors should be exactly the same. Okay, so how do you write this in this form? Now, if I manage to write this into linear combination of these guys, then because of this assumption, it will be 0 on the right side. And if this is 0 for all w, right, and then that would force tu to be 0 for if this is 0 for all u and w, then it will force tu to be 0 for any u because of what we just observed. And if tu is 0 for any u, that means t is the 0 operator, right? So that's how we're going to prove this way. The opposite direction is trivial, right? If t is 0, then of course 0 and v is 0. That's trivial. So that's what we're going to do. And now I'm going to pull off something outrageous. So it looks like t u plus w, u plus w, minus t u minus w, u minus w over 4 plus t u plus wi, u plus wi minus t u minus wi, u minus wi over 4 I. Okay. Yeah, I had to practice this before this lecture because I don't remember this by heart. This actually comes from some identity. I forgot the name.
Polarization identity.
Oh yeah. Thank you. Yeah, polarization identity. Yeah. Okay. Yeah. Where did you see it?
I don't know. It's in some algebra book. I forgot. Hoffman and Kuntz.
Oh, okay.
I read it.
I mean, the first time I saw this was in functional analysis class. So it's like way after grad school. So thank you. Yeah. So this is called polarization identity, except that I have a t added. Okay. So that's true. And just for fun, although the book doesn't have it, let's just see why this does work. It's just straightforward calculation, but you can try this. First of all, tu plus w and tu just u plus w. Well, this is tu plus tw u plus w. And by using linearity of the first argument, you have tu u plus w, and then tw u plus w. And then this second argument is not linear, but it's conjugate linear, right? So addition still splits. So you end up with tu u plus tu w plus tw u and plus tw w. That's what happens. Okay, and then now this next guy, tu minus w, well, that's like exactly this, except w is replaced by negative w, right? So the outcome will be exactly the same, except that whenever you have a w, you need a minus. But this has two minuses, so it's a plus. Okay? So it's going to be tu minus tu w minus twu, and then plus tww. Okay. And now you're subtracting the two, so let's subtract this minus this. So if you have tu plus w, u plus w, minus tu minus w, u minus w, over 4. You subtract this minus this, so these two cancel, but these two double, right? Because you're subtracting a minus and these are the same. You have 2 tuw plus 2 TWU over 4. Okay, so that part is what this gives you. Okay? Now, the second one is exactly like the first one, except that you have an I instead of WI. You have WI instead of W. So I can copy this first result and to have just W replaced by WI. Now WI, when I is in the second argument, the conjugate comes out, right? So you get negative 2I. But this time I is in the first argument, so it comes out without conjugate. And I is multiplied. Negative I times I is positive 1, so you have 2 TUW. Then I times I is I squared is negative 1, so it's negative 2 TWU over 4. And now you add these two, you can see that these two cancel, whereas these two, again, double, 2 plus 2 is 4, but divide by 4, you end up with, you end up with this result that this is indeed TU plus W, TU comma W, right? Okay. So we've just verified this result. And as I said, I'll write down what I said before. This says that TUW is equal to 0 for any UW, right? If I think of So if I think of U plus W as like V and then V, and we assume, we're trying to prove this direction, okay? So because these two are the same, this assumption allows us to say this is 0, that's 0, that's 0, that's 0. So we've shown that TUW is 0 for any UW in V, right? But then, if this is 0 for, if you fix TU and you let W to be anything, then that allows us to say that TU is 0, right? But this is true for all U. So that means T is 0. Okay? All right, so back to this, what we are trying to prove. How does this allow us to show this? Okay, so now proof of 7.15. So what you do is you move this to this other side. So we say T minus T star equal to 0. And let's go this way first. Okay, so proof of this way. Since this is equal to 0, we see that TVV minus TVB bar. So this is our assumption. Okay. Then bar, if you flip these two around, the conjugate disappears. So we end up with TVV and then minus VTV. But then this is same as, well, I can move this T to the other side by putting a conjugate. And then because the first argument is linear with the same v, we end up with tv minus t star vv, which is same as t minus t star of vv. But this is our assumption, right? It's self-adjoint to begin with. So this must be 0 vv, which is 0. Okay. Now, to prove the opposite, see, if this is always real, then this is equal to 0, right? And all of the calculation here would lead to this guy, right? So if TVV minus TVV, if this is 0, that's what it means to be real, right? If it's real, then complex conjugate is itself, right? Those are exactly the real numbers. So if this is true, that's going to say that t minus t star vv is going to be 0 for all v, right? Just by going backwards, okay? This is equal to this, equal to this, yeah. And so since this is equal to 0, this has to be 0 for all v equal to v and v, sorry, v and v. And therefore, from this lemma, we see that t minus t star is 0, which means t is equal to t star, that's self-adjoint, right? Okay, so this gives you a nice characterization for self-adjoint matrices, which is that if you have a self-adjoint matrix, then it's the same thing as saying if you have TV and V, you always get a real number. Okay. T is self-adjoint, then TVV equals to 0 for all V in V, if and only if T is 0. Okay, so this is almost like 7.14, but we've removed something and added something. We removed, sorry. I forgot something when I wrote down 7.14. 7.14, you would see that in the proof we had the I in there, right? So 7.14 is only true if it's over complex numbers, okay? Now here, if you want to have a similar statement for real vector spaces, it's saying that if you want to have a similar statement for real vector spaces, then you need the condition that it's self-adjoint. Okay? Yeah. So that's 7.16. So proof for the base field being C, already done in 7.14. Okay, so we only need to think about the base field when it's R. And for that R, what we do is we have the following identity. It's the same idea, but slightly different identity, which is TUW. This time we're just going to rewrite this as TU plus W, U plus W, minus T, U minus W, U minus W. Wait a minute, we have something extra. Why don't we need that this time? Well, that's because of two things. The reason is that we are working on real vector spaces, and also T is self-adjoint. So let's verify why that's true. Now, if I start with this, we know that this right-hand side is equal to the following: T 2 times TUW plus 2 times TWU over 4. Okay, so that's what we calculated a moment ago. Now what we want to do is we can move this t to the other side as t star, but t star and t are the same because of our assumption. It's a self-adjoint, right? So we have this over 4. And now we swap these two. And when you swap, you're supposed to have complex conjugate, but we're working on real space, right? So complex conjugate has no effect. Real numbers under complex conjugate doesn't change at all. So you just end up with 4 times tu w over 4. Okay, so that's how you prove this. And again, after that, the argument is exactly the same. So that means tu is 0, because this is true for all uw, that implies tu is 0, but that implies t is 0. Okay. So that's like another property of a self-adjoint matrices. I guess, in other words, one way to say it is that somehow being real has a lot to do with being Hermitian.